Welcome everyone. I'm Tracy Fitzpatrick and I'll be your moderator today. Thank you so much for joining us here at Netcom Learning, a market leader in promoting lifelong learning, training, and talent development solutions. We are very excited to host today's event, Building Secure and Governed GenAI Applications with Amazon Bedrock. Presenting today's topic is Francisco, a seasoned machine learning engineer with over 10 years of experience in cloud and AI solutions. He specializes in designing scalable, secure data and AI architectures across AWS, Google Cloud, and Azure, helping organizations turn data into real business impact. With strong expertise in data engineering, analytics, and production-ready AI system, he brings a practical, multi-cloud perspective to enterprise AI innovation. Bear in mind that this is an overview of a very robust topic. We offer a collection of technical and business courses that can be tailored to your specific requirements. If you are interested in a further discussion, you can make an appointment with our learning consultants through our website at netcomlearning.com. Today's session is also being recorded, so you'll get free access to the recording in the next 24 hours via email. Netcom Learning helps customers build innovative learning organizations by achieving a smarter workforce, adapting to change, and driving growth. We do this with a broad catalog of offerings, developing customized learning plans, and our global delivery capabilities. Since 1998, we have been empowering organizations with our managed learning services to help them reach optimal performance results and address challenges. We do have 9 practice areas in which we specialize. They encompass people, process, and technology training. Today's presentation is from the Data and AI practice area. Netcom Learning offers a comprehensive training portfolio of courses for the topic being covered today. Our upcoming classes include various trainings on the given courses. You can also access a variety of marketing assets, such as the free training and blogs, by clicking on the available event handout. These offerings can be found with a simple search on our website at netcomlearning.com. Today's session focuses on how enterprises can securely move generative AI initiatives from experimentation to production. We'll explore how Amazon Bedrock, combined with AWS security, IAM, networking, and governance controls, enables organizations to build GenAI applications that meet enterprise compliance and risk standards. This session is designed to give AWS professionals practical guidance on architecting secure, governed, and production-ready GenAI systems that leadership and security teams can confidently approve. Now I would like to give you a quick overview of the logistics before we get started. To begin with, you do have the option to view in full screen by clicking on the full screen button on the right side of the GoToWebinar viewer. Simply hit the escape key to exit the full screen. Everyone has been muted except for our presenters. Feel free to submit any questions you have for the presenters here in the questions pane, and we will address them at the end of the session. And to get the best out of today's events, we've included the slides, courses we talk about, and marketing assets in the Handouts section of your GoToWebinar viewer. You may refer to them at any time to get a better understanding of today's topic. And we do realize that some of you may have to leave early and want to let you know that as you do leave the session today, you will be presented with a short survey. We would like to request for you to take a quick moment to participate in that survey. Your feedback really helps us understand your learning experience and improve our future sessions for you. The survey answers are measured on a scale of 1 to 5, 5 representing outstanding and 1 representing poor. And now I'd like to pass this over to our trainer to present today's topic. Hey Francisco, thank you so much for joining us today.
Thank you, Tracy. And I'll be your Netcom technical instructor for today's session. Let me tell you a little bit about myself before we get started. My background is in machine learning and data engineering. I am certified in both machine learning and data engineering across the three major clouds, which are Google Cloud, Microsoft Azure, and of course, AWS. Besides being an instructor, I'm actually a full-time machine learning engineer where I have built solutions using some of the technology that we're going to look at today, which is generative AI with Amazon's Bedrock. So today we're actually going to dive into this topic, which is at the forefront of cloud innovation. We're going to look at building secure and governed generative AI applications with Amazon's Bedrock. Amazon's Bedrock is essentially their machine learning development platform for traditional models and generative AI models as well. As generative AI moves from experimental proofs of concepts into production environments, the focus needs to shift heavily towards security, governance, and architecture. So over the next 2 hours, we're going to unpack exactly how you can take these powerful models and integrate them into your enterprise system safely and effectively. So let's get started. Now, before we jump into the technical details, let's take a look at our agenda. So you know exactly what to expect from our time together, we're first going to cover how to build agent-driven workflows using AWS AI services and serverless compute. Then we will discuss how to design multi-agent orchestration patterns specifically tailored for Amazon apps. Then we will look at the practical steps to integrate foundational models using Amazon Bedrock with AWS Agent Framework. After that, we're going to shift our focus to operations, discussing how to deploy these agents with a focus on scalability, observability, and cost optimization. Because security is paramount, we will dedicate time to learning how to secure these AI agents using IAM, which is Identity Access Management, network controls, and building responsible AI guardrails. Finally, we're going to put this all together by applying real-world architecture blueprints to an AWS native agent system. Now, let's jump into our first major topic. Here, we're going to explore how to build an agent-driven workflow using Amazon's AI services and serverless compute. When we talk about serverless in the context of AI, we're talking about removing the operational burden of infrastructure so we only focus on the AI's application business logic. What do I mean by this? Well, I mean, we're not going to focus on which hardware we use and how to scale it. We're going to rely on Amazon's Bedrock to do that heavy lifting for us so we can just focus on improving our AI solutions logic and decision making. Now, before we start writing a single line of code or provisioning any services, we must have a solid plan. Planning a generative AI project generally has 4 critical steps. Step 1 is defining the scope. This is when we need to get a deep understanding of our customers' needs. Are they looking for summarization, a conversational chatbot, or an intelligent data AI data extraction tool? Are they looking for an agent that can perform tasks such as create slides or make bookings? Once we've defined this, we need to consider the organization's capability. 1, do they have the necessary cloud engineering talent to develop on AWS? Do they have their data in a single location, such as a data lake or data warehouse? Once we define this, we're ready to get to our next step, which is selecting the data that we need and the model. This involves taking time to identify and curate your enterprise data. Now remember, artificial intelligence is only as good as the data it has access to. So that means we need to prepare the data. Once the data is prepared, we can select a pre-trained model that aligns with our specific workload requirements. After this step, we look to adapt the model. Very rarely we take a model completely out of the box for enterprise tasks, meaning that we just don't download GPT or call the GPT API and suddenly we use it for business tasks. No, we need to adapt our model to our enterprise. This means we can adapt it by applying prompt engineering techniques, augmentation techniques, and taking our time to customize the model through fine-tuning or building subagents to help that model take action. Then we have our fourth step, which is to finally use the model in production. Here, we need to think about responsible AI concerns to ensure fairness and safety. We must continually track the performance of the model to avoid model drift, meaning that as time goes on, it degrades in performance. We want to avoid that, but also ensure that our model is always acting in a safe and secure manner for us and our customers. Now, let's simplify things by looking at the foundation. A foundational model is a core of generative AI applications. This is a simplified view of the core application components. First, we have what we call the application front end. This is where your end user actually interacts with the system. Behind the front end sits the application logic and foundational model interface. This acts as the bridge between taking that user input from their prompts in a way the model can understand. And finally, we have where the foundational model sits. This is where the heavy lifting, the heavy logic is going to occur for text generation, video generation, code generation, audio generation, or whatever task we decide to give the model. Now, as our application matures, that three simple step architecture won't be enough. We have to move forward to integrating our enterprise data and complex workflows. Alongside our core application component, which were the application frontend, the application logic, and the foundational model interface, and of course the foundational model itself, we introduce an optional application component to give the AI context and agency. This can include enterprise datasets for grounding the model, embedding models to help convert text into vectors, vector stores to provide more efficient semantic search, memory to maintain conversational history, and agents to execute multi-step reasoning tasks. As we add these pieces, we need to think about our governance and security that has to be integrated in all components at the very beginning, not at the end. So we always have to be thinking about access and security at each stage of the model, not just a final stage when the model is ready to go. So let's take a look at this diagram, which shows a basic generative AI application. This is an extremely simplified diagram. Here, the user interacts with our application frontend. The frontend communicates with Amazon Bedrock, where it's leveraging a foundational model. This is great for a quick proof of concept or a hackathon project. It tightly couples the frontend to the Bedrock API, but it lacks the middleware required to build a truly scalable, secure solution. What we're going to see soon is how to add scalability, security, and logging features to our model. To build for production, we want an architecture like this example, serverless. Here, the user accesses the application frontend. The frontend might be storing its static assets in a Amazon Simple Storage Service or S3 bucket. When the user submits a prompt, the frontend makes an API call through an Amazon API gateway, which gives us the throttling, authorization, and routing that we need. The gateway then triggers an AWS Lambda function. This function contains our business logics. The AWS Lambda then securely communicates with Amazon Bedrock and the underlying foundational model. This decoupled serverless approach allows each component to scale independently and securely. Now, let's map these real user interactions onto this architecture by looking at a conversational interface. In step one, the user asks a question or inserts a prompt, which is, what is a good place for pizza in the city? In step two, the application frontend passes this to the Amazon API gateway. At this stage, we inject contextual metadata, such as the user's location, like is the user in Seattle, if they chose to share location. In step 3, AWS Lambda starts to process this. It might also check an Amazon S3 bucket or the conversational history in memory to get more context about it. For example, if the user has a favorite slice of pizza, dietary requirements, or if they've eaten at that location recently. Using all this, it actually passes the fully contextualized prompt that the user gave us to Amazon's Bedrock foundational model. The model will then respond with the best possible answer. In this case, try Cyril's Pie, which would be the suggested pizza store in the city. Now in this section, we're going to take a look at how to design a multi-agent orchestration pattern for enterprise apps. In the previous section, we have already established the architectural basics that we need to build a more complex solution and develop a more complex multi-agent approach. When moving to enterprise level, things get complicated quickly. We face several distinct enterprise AI integration challenges. Some challenges include, but not limited to, legacy system compatibility. This is when our AI needs to talk to old systems, old data sets, or on-prem databases. Quite often, these systems were not built to integrate artificial intelligence. So they might have limited technological capabilities to communicate or integrate with AI. Often, these systems also face strict security and compliance requirements. This limits our ability to use that model safely or to even interact with the dataset. They can also come with massive scalability concerns since they are on-prem, so it's not that easy to scale up to more servers or computing power, and they will have issues maintaining data consistency across distributed systems when we pass it to our systems. So to tackle this, our solutions must include some sort of API modernization, establishing a rigid governance framework to maintain security and compliance, utilizing a robust cloud architecture to improve scalability, and relying on proven integration patterns to make sure that we add to our orchestration design the smoothest way possible to integrate our applications, data, and any other additional feature or appliance we need for the model. This slide now provides a AWS integration architecture overview of the core services we need to build out these enterprise solutions. Here, we're going to rely on Amazon's API gateway to provide secure API access. So this means that any request we make to our Bedrock foundational model is actually secure and encrypted, meaning that it limits man-in-the-middle attacks or your data being leaked. Then we're going to use AWS's Lambda as our engine for our serverless logic. This is where we're going to host our business logic for the AI solution, but also give us that serverless capability to scale rapidly. Then we're going to use Amazon's Event Bridge, which handles our event orchestration. Then what we're going to do is we're going to store our data using Amazon DynamoDB for our NoSQL database and Amazon RDS, which is Relational Database Systems, for relational data. Finally, we're going to secure our network using Amazon VPC, Virtual Private Cloud, and manage our user identity service through AWS IAM Identity Center. Remember, IAM stands for Identity Access Management. So using all of these technologies, we will now be able to build a strong data AI enterprise application that meets our security, reliability, and accuracy requirements. So a strong cloud architecture demands a solid RESTful API. So now we need to think about our RESTful API design patterns. So if we look on the left, we have our client applications. They can be web, mobile, or other AI devices. This application layer should be able to send the requests that the user to their mobile, web, or other AI solutions would like to send to our system. Then it will hit our RESTful API gateway. This gateway strictly manages through HTTPS and HTTPS methods secure handling of our requests. GET requests will usually result in a 200. Post handling error requests will usually result in a 400 error. And then requests dealing with server errors will be handled with a 500, as well as delete methods. At this stage, all traffic is routed to specific endpoints. For example, if we want to generate content, we can actually send a request to an endpoint that's called generate content using a post method. If we wanted to get our current ID or any information related to us, we can use a get method by calling that specific endpoint, such as our status ID endpoint. This is processed by a stateless AI processing layer, where independent discrete operations follow a standard request to process to response cycle. So a request gets sent, it gets processed, and then the response is returned to you. When dealing with AI service integration patterns, it is an architectural best practice to never have your app call Bedrock directly without a buffer. So we need something in between. So this is where you should place an adapter layer between your internal system, which would be your app, and the Amazon Bedrock API. Why do you want to do this? Well, this is because the adapted layer is perfectly positioned to handle authentication, data transformation, error handling centrally, ensuring your application logic remains clean and secure. For example, if we're sending a request, we first want to make sure that user has that right to send that request, right? Like they are an authorized user of our platform. Our adapter layer can handle that before it touches the model, in case the model might respond with inappropriate information or information that user shouldn't be accessing. So our adapter layer stands in between to make sure that there are no faults. And if there is a fault, it shouldn't actually reach our Amazon Bedrock API. So this is where a lot of authentication, data transformation, error handling will be handled. So we're not overloading the Amazon Bedrock API with poor requests or potential errors. Now let's talk about event-driven architecture fundamentals. For scalable asynchronous tasks like processing thousands of documents, we need to look at event-driven architecture fundamentals. This starts with event producers, which can be AWS services, like custom apps, Internet of Things devices, or third-party systems. These producers fire off events to our event router, which is Amazon Event Bridge. This will act as our central event router. What Event Bridge will do will evaluate the rules and routes the event needs to be sent to using the appropriate event consumers. Those are the event consumers are what's going to receive the request. This could then trigger a document processing pipeline, kick off content generation windows, or update analytics and monitoring systems, or alert to any unauthorized access. So essentially, this is where we send a request to, where it will be sent then to the next step of our journey, depending on what that user request was. Now we're going to get a little bit more hands-on in this section. We're going to learn how to integrate foundational models, specifically Amazon Bedrock, with AWS Framework Agents. This diagram maps out an integrate example agent configuration running within AWS Cloud. So let's trace this flow carefully. First, we have the client application. The client app will send a prompt like, where's the best place in the city to get a pizza? It then passes through a guardrail. In this case, the guardrail is going to ensure that the user is asking something that they are allowed to ask. For example, if the client that is asking for some sort of investment advice, like should I buy the stock, our investment advice guardrail can check, should I even answer that question since I'm giving them potential advice that might impact their finances? If that question is allowed to be asked, the guardrail will then pass it through the next stage. The next stage would be our banking assistant agent. This agent will act as our reasoning agent. So what do we mean by that? Well, it means it can decide to generate a task to search for the content of frequently asked questions, which is backed up by our OpenSearch serverless index. So the banking assistant agent is responsible for allocating the prompt to the correct task. If it's a frequently asked questions task, it'll go there. If it's a task that requires more thinking, it could potentially go to Amazon Bedrock. If it's a task that needs to go to a customer support group, hence a human agent, then we can actually do that as well. If it were to go to a frequently asked question knowledge base, we want to store that knowledge base in something like OpenSearch, right? Because OpenSearch will allow us to connect documents that have the answers to those frequently asked questions, and it will help generate the correct response to that user. These documents can be stored in an S3 bucket, and they can be read through Amazon OpenSearch. So Amazon OpenSearch and the S3 bucket will act as a database that our model can use to answer frequently asked questions. Now, of course, if it's not a frequently asked question prompt, perhaps the agent might need to decide to push it to a customer support action group. This can trigger a Lambda function. The function can perform, let's say, 2 tasks. One task might be, let me actually respond to the user with the correct response to help them with their support question, or pass it off to a human agent. Quite often, AI systems will still include human intervention in case the topic is too complex or too sensitive to be handled by the AI. Throughout this process, task prompts are continuously processed and evaluated by Amazon Bedrock. So essentially, Amazon Bedrock will be our foundational model that our Lambda function will still have access to. And remember, our banking assistant agent is using Bedrock to connect to a foundational model like GPT. Once all this has been performed, the banking assistant will then return the response to the investment advice guardrail. Why do we need the investment advice guardrail again? Well, we need it again because it needs to make sure that the response it's going to send is accurate, safe, and meets all the requirements to send to the user. If it does not, very likely it will fall back to a default response like, please ask again, or we need more time, or we can't answer that question right now. So you essentially have the investment advice agent perform 2 guardrail functions. One, make sure that I can answer the question. 2, once I do answer the question, do my last level of check to make sure that the response I'm sending back is useful for the user. So again, those would be our 2 guardrail responses. Now, let's talk about the code to create the agent. What you see here is an example Python code required to actually create an agent. So let's start at the top. First, we're going to format a knowledge base ARN using our region, account ID, and other IDs as well. So knowledge base ID. What this is doing is that essentially we're giving it a client that it can call and create the agent. So we're essentially authenticating ourselves here, saying we're going to use this region's resources on this account on this knowledge base ID. Then below it, we have our create agent function. Our create agent function takes key parameters like agent name, agent description, agent instructions, inference profile, foundational model, and knowledge base ARN. For short, we'll just call it KBAR. Now, what are we doing here with these parameters? Well, one, we need to know which agent we're going to call. Because quite often, enterprise applications use more than one agent. You never really just have one simple agent that does everything. Like you saw before, we had a banking assistant agent, and then it passed it off to different tasks. We had our investment advice agent that did our first level of checks. So quite often, we might need to create an agent within an agent to have to solve specific tasks. Then what we do is we define the steps of that agent. So for example, we define what are the system instructions, what is the description of that agent, what model it's going to infer, whether it be GPT or Gemini. And quite often when you build enterprise apps, you don't actually have to use just one model. You don't always have to stick to GPT. You don't always have to stick to Gemini. You don't have to stick to Claude. You can switch it depending on the task, or you can switch it dynamically. So once our agent is created, we give it a little bit of time to wait to answer a response. Why do we give this time? Well, essentially, the reason we give that time.sleep is just to make sure that we're not overloading the server with too many requests at once, and we're also giving that model enough time to respond correctly. Now, you'll notice that we have a parameter called idle session TTL in seconds, 1,800 seconds, which is effectively a 30-minute memory window. So what's going to happen is the first time you call this agent, you will trigger that 30-minute memory window. This will create a session. The session will then make sure that any information within that session, such as the previous conversation, the continuing conversation, is accounted for. If that session is idle, meaning that the user has not returned or made a request or prompt or downloaded or performed a function within those 30 minutes, the session will expire, meaning that that context window for that session will be closed. It potentially could sit in memory that we can call, but that session window will be closed. This is just not to overload our servers. So you always have to think about what is going on when the user is not doing anything, which is quite often an issue. Now what we're going to talk about is adding our agent the ability to do things. What do we mean by this? Well, quite often we think about generative AI solutions as returning text because we're used to interacting with some sort of chat or text interface. But we actually might want to perform tasks like make a booking, buy that stock, order that pizza. And this we'll do by creating an action group with the Lambda function. Here what we're doing is we're defining our function schema in JSON. So as you can see here, we have an action to get a function called getAccountBalance. And what it's meant to do is return the available balance. So what we do is that we specify the parameters we need, which will in this case be the user ID. Then we will pass it to the Lambda function so we know which user to collect the balance from. We can also define another action, like book an appointment. Here we will use the add action group to the Lambda method, passing our schema, our Python file lambda function.py to attach this logic. And now our agent knows how to interact with the backend. So what we're doing here is that we're just not building one function. We're building several that are going to be part of this action group. This action group is related to banking backend services. So the benefit of this approach is that, remember, our agent's not just going to return a response of text. It's actually going to go into the balance, authenticate itself, and withdraw the necessary information to respond to that user. This is what we would call the action, right? Because it's not just returning text and responding. It actually has to do some sort of authentication, get the account balance, and any other parameter we want, like book an appointment. This is what we meant earlier when we said, are you building just a conversational agent or an agent that's going to perform specific tasks? And the way you can define the tasks is through the action group and through the Lambda functions. Now, we need to give our agent information. We need to give it a knowledge base. So what should a knowledge base be? Well, remember, each agent will have its own domain-specific information. And then we will add that own domain-specific information to the agent. Here we use the associate agent knowledge base method, providing the agent ID and ensuring the knowledge base state is set to enabled. This means that we're now allowed to use the knowledge base because you might not always want to enable the knowledge base, particularly if there's inaccuracies with it or any sensitive data has been discovered in. Next, what we're going to do is we're going to give it a clear description, telling the agent to access the knowledge base when the customer talks about investing. This is going to serve a little bit as an intention. So should the agent always access the knowledge base? For example, what if the customer asks what time of the day is it? Should we really be going to a knowledge base to answer that question? Probably. But what if the agent asks about investing, saying, what should I invest using my current balance and portfolio? Well, the description makes it clear when that knowledge base should be activated in that scenario. So if it is an investment question, the customer will be able to access the knowledge base. This is important to make sure you're not always accessing the knowledge base because the knowledge base actually takes up time. And remember, it needs to index through that open search that we saw a little bit earlier in our diagram and figure out what information from there it needs to collect. So it is essentially doing a research task. So we don't want to overload it by having to do that task to a relatively simple question like what time of the day is. So once we've defined our knowledge base, we essentially call the prepare agent function. And from here, we actually create the agent alias and test our setup. And we should have it working ideally perfectly the very first time. So now we're going to transition to deploying agents with scalability, observability, and cost optimization. Let's talk about token processing requirements. Why do we need to talk about this? Well, quite often, large language models and generative AI solutions charge you per token. A token is approximately a 4 characters. So for example, the word for, FOUR, would be approximately 1 token. I say approximately because this is not a strict rule. It's possible that the hashtag symbol could be worth 1 token. Now, to ensure our architecture can handle production traffic without latency spikes, we must perform a token processing requirements calculation. This is where we're going to carefully account for the number of input tokens and output tokens we need. What do we mean by input tokens and output? Well, input tokens are essentially the questions or prompts we give to the model. Each of those 4 character words, again, approximately, is going to count as a token. So if we give somebody a 1,000 token window, they can approximately only use 1,000 tokens, which is approximately 4 character, roughly around 4,004 character words, right? So that means that we're limiting the response. If we give them, let's say, a 100 token window, that means they can limit to roughly around 400 token output. So that means that the answer the model will give will be short. So we need to really deeply analyze historical usage patterns, requirements to rigorously plan for our peak loads. This is important because not always do you need to give a lot of input tokens, but you might need a lot of output tokens. For example, if you were to write a prompt like, give me an investment strategy for buying gold, then you might need quite a large amount of output tokens, but not that much number of input tokens. It's important to also understand that descriptions and knowledge bases that we talked about before do impact our input tokens. So not only do you need to analyze historical usage data pattern, but you also need to analyze any tokens you might be using from your knowledge base or from your system instructions. So to find this baseline, we use this formula. The formula is, for total capacity requirement, is request per hour times average tokens per request divided by 3,600 seconds. This formula will give you a very good baseline. And I stress the word baseline because it might not be a hard baseline that is going to be strict every time. So quite often you might need to adjust your token calculations and adapt to longer prompts or longer outputs and try to find a balance between each dose because you are charged per token. So the more tokens you use, the more expensive this will be for you. And remember, you do actually have a token limit depending on large language model. Different large language models give you different limits of input tokens and output tokens. So finding your baseline using this formula is a very good idea, but remember your baseline will very likely adjust. So you quite often, maybe once a week, once a month, depending on the usage of your application, want to review your token requirements. Now let's discuss auto-scaling policies. When designing auto-scaling policies for your AI workloads, you must balance responsiveness with cost. Keep these core 3 strategies in mind. One is predictive scaling. This should be the queue depth and traffic patterns to proactively add resources before the user experiences downtime. So here what we're doing is we're building some sort of solution to scale our infrastructure, our computing, or our storage. This will make sure that we account for any potential higher usage. So it's almost like our upper band of CPU and data storage. After we have scale triggers, this needs to be highly responsive to prevent queue buildup during sudden and unexpected traffic spikes. As your solution gets more popular, the number of prompts being sent or requests being sent could build up. You don't want that buildup to cause a lag on your system, to create a crash, or to impact negatively the user experience. So you need to make sure that you have scale out triggers that can handle this unexpected spike in traffic. Then, of course, you have scaling triggers. Conversely, a scaling trigger should be conservative to avoid thrashing and ensuring you don't prematurely kill resources while you wait for another wave of traffic to hit. By using these 3 elements, you should be able to define a auto-scaling policy that makes sure your AI workload doesn't crash. The good news is that AWS Bedrock does have strong predictive scaling capabilities. So AWS Bedrock will normally request for you to tell it what is the limit of the computational power or storage that you want to give it. Say, for example, you want to give it a limit of 148 gigabyte RAM machines with 1 terabyte data storage. That doesn't mean that your solution will always use those 100 machines. It means that it can scale to 100. So if you have 1,000 users on your platform, and let's say that can be handled with 10 machines, but suddenly you have 1 million users on your platform because of popularity rise, now it can scale up to all those 100 machines and handle the traffic load without crashing. The scale out triggers will make sure that you don't get a buildup where people's responses are taking longer. In today's world, we really don't want to spend too much time making the user wait. So it's important that we make sure that we account for those traffic spikes by telling it to increase the resources as quickly as possible, or when our solution indicates that we might need to increase those. But of course, we also want to scale back those resources so we're not paying for full price of those resources when we don't need to. So AWS Bedrock actually takes care of a lot of this for you. It will dynamically scale up and scale down depending on current usage, so you don't actually need to worry about creating that business logic. So now let's talk about the concept of token economics. If you want to manage costs, you must master token economics. Understanding token economics in production systems is vital because token economics form the foundation of AI monitoring. Remember, your input token represents your prompt, your output token represents your generated responses from your artificial intelligence. Different workloads will have different token ratios. For example, a QA system might have a 1-to-1 ratio, but a summarization task might have a 10-to-1 ratio. It's very important to understand how many tokens you would need at the input level and the output level. Now, why do we talk about token economics? Well, it's not just about using tokens. It's about making sure you don't use tokens when you don't need to. What do I mean by this? Well, let's assume that approximately each token costs you $1. If someone asks a frequently asked question, for example, what is the best stock to buy for tech stock? Let's assume you've already answered that question. This is when you should use your memory system to take that previous text response to answer that question. Let's assume someone asked a more straightforward question, like, where is the location of the bank? The location of the bank is not going to change at any point in the near future. So why use another set of output tokens to answer that question? What you want to do in this case is that you want to take the input tokens the user asked from the first time another user asked the same question and identify that that user is asking the same question. And instead of returning a generated AI output, you returned a cache response. You potentially could even use an AI system, like a subagent, to return that cache response. And it will use less tokens because it knows already the answer. So it says, oh, I don't have to search for it. I don't have to formulate another response. I'm just going to copy paste. But it's ideally better if you have some sort of memory cache system that answers previously asked questions, if that question's answer will very likely be the same answer each time, such as the bank's location. This is really important because this allows us to account for our token economics and make sure that we're using tokens efficiently and effectively while keeping costs low. Also remember that token consumption impacts latency. If you're out of tokens, say for example, your application has a limit of 1 million output tokens across all users, and if you're out of tokens, your users will experience a delay in response because they are waiting for those tokens to be regenerated. Now let's discuss configuring a model invocations and logging. So what do we mean by this? Well, very simply, we're talking about we cannot optimize what we cannot see. Here, what we're saying is that logging or monitoring is a mandatory step. You can do this from the Amazon Bedrock console. Here, you want to enable model invocation logs. This can be immediately enabled once you launch your model. What these logs do is give you an incredibly detailed account of what prompt was captured, how many input tokens were used, how many output tokens were used, what model parameters were used, and the precise response latency. We can then use this to fix our model, maybe adjust our token economics, account for errors, or make our model faster. The good news about these logs is that they're automatically shipped to CloudWatch logs. CloudWatch serves as our secure log storage and allows us to view error details of a specific model version used. The great thing about CloudWatch is besides giving us that storage, it actually gives us a very easy way to navigate through our data and look at our logs. Quite often looking at logs is a tedious, cumbersome, and annoying approach. But CloudWatch logs allows us to index searches, gives us visualization of errors, and even identify problems before we even have to review the logs, making it easier for us to deploy our solution. CloudWatch Insights give us the ability to perform the deep analysis and queries for our AI model, helping us adjust traffic, model requirements, CPU requirements, storage requirements, or maybe even design requirements as well. Now, we really need to understand the cost challenge. Generative AI brings a unique operational expense structure. So, by understanding the cost challenges that we're going to face, we're able to provide a better solution that's both cost effective and retains high customer satisfaction. So, the number one element that we need to look at is understanding the challenge. We must deeply understand how token-based pricing impacts our business model. For example, is your model returning text or is it returning some sort of content like video or images? Why is this important? Well, remember how I told you approximately 4 characters equals 1 token. 4 text characters equal 1 token, approximately. A video model is not priced there. Again, depending which model you use, but quite a lot of the popular ones use somewhere between 8 to 15 tokens for creating a single frame. And if you're creating a video, you're going to need a lot more than just a single frame, even a lot more than 2 frames. So you have to understand how the token pricing is impacting your model. By knowing where do I need to save my tokens for, is this solution going to create text and video, text and imaging, text and code, text and audio, or all of them together? Then you need to think about how you distribute your tokens equally across each one, or maybe not equally, depending on which one will be used the most. So when you understand this challenge, you'll be able to design your token strategy based on your specific model. The only way you can really understand what's going on is by analyzing token usage. This is where we would use both billing reports and CloudWatch. CloudWatch will tell us what prompts are being written, and billing reports will tell us how much it's costing us. Here we'll strictly monitor input and output costs. By looking at token usage, we can see, hey, can we create a potential caching system, or can we somehow get the user to write less? So we potentially could say to the user, keep the response to 5 or 6 words, or even just add some sort of front end limitation of how many characters they can write. This will only come from analyzing the token usage. After that, we can implement optimization. Have you implemented architectural techniques and best practices to reduce overhead? For example, that character limit that we discussed about. But you can also rely on Amazon Bedrock to do a caching system for you. This is one of the great things about Amazon Bedrock. It can recognize if the same prompt is being asked several times and then just cache the responses by default. So this way, you're not using output tokens again to save your costs. It can also even give suggestions on how to use your token distribution. But don't always just think about the tokens. Think about what other elements you can use to improve the model performance. For example, we talked earlier about the memory caching system. Maybe we can actually already have pre-suggested images if the user wants to create an image based on previous conversations. That way we're controlling the token output, not so much the user. Then, of course, we need to talk about achieving viability. The goal of this is to achieve predictive cost scaling, so finance doesn't get a surprise bill at the end of the month. The good news is that both Bedrock and Amazon Billing actually do predictive modeling of our token usage and our cost usage. And even better news, it actually does give you suggestions on how to reduce your costs. Because by reducing our costs, we're able to make sure we can meet the customer satisfaction requirements while not hitting very heavily in our cloud bill. Let's take a quick 5-minute break, and then I'll start on the remaining topics after this break.
Sure, we are now going to take a 5-minute break, but before we do that, we are going to launch a quick poll that we want to invite you to participate in. Doing so helps us know how we can better serve you by telling us who might be interested in more information or in taking some additional training. In addition, we have a lot more informative webinars coming up, so please go to netcomlearning.com/webinars in order to register.
Welcome back, everyone. Let's continue from where we left off. So let's now talk about cost performance optimization. When we actively apply cost performance optimization techniques, we typically see a massive 30 to 50% cost reduction. This optimization pipeline involves three pillars. First is the model selection, which ensures efficiency matching. Essentially, what we're talking about here is picking the right tool for the job. For example, different models have different costs, right? That means that if you are doing a summarization agent, should you really be using a full general LLM model? Probably not, because then this summarization agent will cost you more for a fully generalized LLM model. Remember when I told you that approximately 4 characters equals 1 token? That is not true for all LLMs. However, most follow that approach. But if you use a summarization specific only model, it can actually be more cost effective. So it will use less tokens to achieve the same response or use the same amount of tokens at a lower price because it has a more limited range of applications. After this, we talk about token optimization, which we discussed earlier. Remember, the token optimization relies a lot on caching to avoid generating tokens to answer the same question types, and also limiting the number of input and output tokens that we can give to the user. For example, if we're asking the user if the user would like to output a video, maybe we limit the number of frames or pixel quality that we give in that video, which will limit the number of tokens. If already a previous video was created that is very close and similar to the customer's request, you can take that previous video as a example output, adjust it minorly using the new tokens. That way you're not increasing your token cost by creating a brand new video, you're just adjusting a pre-created video to meet the customer's requirements. And finally, the third pillar is infrastructure management, which focuses on smart scaling resources. Remember, costs are not always tokens. The cost can be computational resources, data resources, and network resources. For example, if you have to enable a middle layer for throttling, you might need to think about, okay, when do I need to activate this middle layer for throttling issues, and how much should I handle? What's the throughput I can handle? Is there a limit I should have? Do I need to limit the number of users on the site, or do I need to potentially create different networks across the world to handle this workload? Quite often, when you're looking at cost optimization, one of the best pieces of advice is to think about it long term. The reason we think about it long term for infrastructure and token optimization and model selection is because a lot of the cloud providers like AWS could give you actually a very good long term deal if you commit to a certain level of usage, which would be cheaper than on demand. A lot of these cloud providers do provide both fixed term pricing, which requires a minimum usage across these three pillars, or on demand pricing, which usually seems cheaper, but it could have hidden costs or long term costs that you're not accounting for. For example, let's assume you did on demand pricing and you're thinking, okay, my infrastructure meets my requirements. And then with on-demand pricing, you've only been using 5,000 users using your platform, but then you have a spike and you get to 2 million users. Now your usage cost has increased. So maybe you don't need 10 machines anymore, you need 1,000 machines. And now you're paying for 1,000 on-demand pricing. However, if you were to go to AWS and you were to say for infrastructure scaling, hey, I might actually need 1,000 machines. What if we agree to a fixed price right now and I don't pay the same rates as on-demand pricing, but you're guaranteed that I will use these 5,000 machines for the next 5 years? Amazon will give you a relatively good deal related to this, and you would actually spend 50 to 30%, sorry, 30 to 50% less money in the long run. Same is true with token optimization. You can potentially use caching systems or use databases with already pre-built answers for commonly asked questions to use instead of creating new tokens. And now with model selection, like I said a little bit earlier, you could potentially use a more specific model with fewer capabilities, but it matches that particular request. And remember, your AI system usually will contain more than one model. Now let's talk about context window optimization fundamentals. A quick but critical tip on context window optimization fundamentals is think of your context window as a prime real estate. Elements like your system prompts, recent conversation, and user current input provide the most value. What do we mean by this? Well, let's assume that we're talking about creating an investment tool, right? And in my previous investment history, I am quite risk averse. So my context window can contain this information, such as in my previous conversations history, I could always be mentioning risk averse. This actually really helps the model understand what's going on. But it's not just previous conversation history. You can actually create a customer profile and pass that to the model as a text or PDF, ideally .text because they will require fewer tokens to process. And you can use that to create a blueprint of how that customer wishes to behave. This then creates better responses for your model. And then, of course, you need the current user input because that is the most relevant prompt at the moment. What using these context windows does is that it'll take old conversation, what seems like redundant information, and pass it to the model to add the best possible answer. This means that you need to manage your available space for storage because remember, if your solution has been used for a while, you don't have unlimited memory storage. I guess your only limit is how much you're willing to pay, but in general, you will have some sort of memory limit because you don't have infinite resources. Now, also remember that the longer your conversational history is, the more input tokens you use. Because remember, conversational history and context windows do eat into your input token count. It's not just the prompt the user writes that counts as your input tokens. It's actually everything that goes into that prompt, such as conversation history, system instructions, context window parameters, or other information like text, documents, all won't be part of your input window. So you need to make sure that you leave enough space for your tokens and also use the most relevant information. And there's different techniques on how to do this to optimize your context window. But just like anything, you don't have infinite resources. So let's take a look at how we can do prompt compression. Let's see the example here. Now, on the left, we have a prompt, which is something that we're going to send to a model without optimization. This is approximately 160 token prompt. So the prompt says, please analyze the following customer feedback and provide a detailed summary of the main themes, sentiment analysis, and actionable recommendations for improvement. Now, this is costing us 116 tokens. And even if cost was not an issue, we are losing some tokens in our context window, right? Because if we're adding any previous context window information, along with this prompt, we're actually already using up 160 tokens for the prompt alone. And remember, there's always an input limit of how many tokens you can add to an input window. Now, by analyzing what the model actually needs to understand the intent, we can compress this into a 64 token response. So for example, we could say, analyze the feedback, themes, sentiment, and recommendations. This simple rewrite yielded a massive 60% reduction in tokens, meaning that we're using a smaller context window, we're lowering our costs, and we're still going to get the same quality as response. What are some key words in the before section that we didn't need? Well, one is the word please there. This model does not need to be asked politely. We could easily remove this word from here. Do we need to say to analyze the following customer feedback? We just need the word analyze. Whatever data we pass, it knows it needs to analyze that data. Provide a detailed summary of the main theme, sentiment, and analysis. Okay, do we need to say detailed summary? Or do we just need to say the main themes and analysis? And provide recommendations. We don't need to say actionable recommendations for improvement. So by just simplifying what we need for this model, we can limit the number of input tokens and give us more output token response and limit our input tokens. So here we're getting a better answer for a shorter amount of words. So it's basically like saying less. And also a key thing to remember, not all tokens are just for one user. If you have a 1 million token context window, that is shared across all users in your application. So token compression is actually very important. Now let's talk about right-sizing models for our use case. In this matrix, we visualize the concept of right-sizing models. Here we must plot your workload against a cost task complexity. For relatively simple tasks like classification summarization, you should use smaller models. These are fast and cheap. When dealing with complex tasks or creative works, we must leverage larger models. So for example, using a massive 100 billion parameter model just to classify an email spam as not spam is a waste of resources. Let's think about a couple examples for this here. So let's say I need to determine if this message is spam. For example, I got a message relating to a great investment opportunity and I just need to deposit $10,000 to be able to enable it. It could be spam. So should I use the largest Gemini or GPT model? Unlikely. I should use a smaller model with a smaller context window, smaller token window, and it will respond faster. Remember, if you want to be alerted to something spam, you kind of want to know right away. You don't want to go too deep into the spam journey before you realize it is spam. But now what if I wanted to ask a more complex question like, here's my product portfolio, here's my investment goals, come up with me for a 1 year long investment strategy to get 30% return. Now, this is not a simple request. This is a request that might take a human user several days to complete, maybe a week or more. So a model can obviously do this, but it needs to think about what it needs. So would we want to use the highest level Gemini model and GPT model? Very likely, because there's not just one action to this request. Unlike our spam and not spam, there's really only one action and there's only one task. Tell me if you think it's spam or tell me if you don't. But here we're coming up with an investment strategy, which will probably require some sort of accounting analysis, some sort of stock analysis or commodity analysis, some sort of investment plan, some sort of risk analysis, and some sort of implementation strategy. Again, this is not going to be handled by one model, so you will probably need a large model or maybe several large models to put this all together. So determining the task complexity and the cost of it. Why do we talk about costs here? Well, remember that cost plays a role. Larger models generally tend to cost more. So we need to think, how complex is this task? And do we need to use a large model? And if yes, how much of this large model do we need to use? Should we use the most amount of tokens, context windows, and such? Should we do a fixed price? Should we lock in a long-term price? Should we use on demand? Should we use a combination? This will all determine what is our cost limits and how complex the tasks are. So a proper solution will quite often require us using multiple small and large models. You can play around with these and determine which model is best for you, and very likely you'll use a combination of different models to put together. One typical advice I give when it comes to cost is why not have the smaller models do some of the tasks and then pass the output of those tasks to a large complex model where you can use maybe a medium-sized model because the smaller models did the tasks, rather than just giving one large model, which are usually more expensive at per token cost than the smaller models. So smaller models do some of the tasks. They pass it to a medium or large model. So that large model does a small level task. And different LLMs have different sizes of models. Some will have a 1 billion parameter window. Others have a 100 billion parameter window. So the higher the number of parameters, the larger the model is, which means it can handle more of a wide variety of tasks, and it can potentially be better solutions, but they will also be slower. So now we're going to transition. Here we're going to look at the final stretch of our class. We arrive arguably at the most important topic. How are we going to secure our AI agents? Well, we're going to look at how identity access management, network controls, and responsible AI guardrails can help us. When working in cloud or AI, we must follow the principle of least privilege access. We highly recommend implementing a hierarchical permission structure, starting from our root account, where you split duties. So, for example, you might have a machine learning admin managing a team of data scientists, machine learning engineers, training, and inference team, and we give them the correct permissions. Let's think about this for a second. Our root account would be probably our top level cloud project. Our machine learning admin could be the person responsible for the team. Now, if you are part of the data science team, which means that you're probably going to do some model research and experimentation, you're probably going to do some data set preparation for our training of our models, you're probably going to do some sort of analysis preparation. Does that mean you should get access to the machine learning deployment pipelines? Unlikely. You can, of course, but you shouldn't. Because remember, we follow the least privilege access principle. So only have enough to do your job. Sometimes people disagree with this because by limiting permissions, we sometimes have to wait for permissions if we realize we need them later. It limits our total view of the solution. However, this is key for security. Quite often, organizations will give too much security, and maybe a data scientist might execute a piece of code that will deploy a change to our ML engineering pipeline, and it will cause it to crash. So by applying the least privilege access principle, we're ensuring that does not happen because the data science team does not have the capability of doing that. Now, who makes these determinations? The machine learning administrator. They will understand with the data science team, the ML engineering team, what are the tasks that they need and what is the level of access they require. And quite often in a real life project, you will probably need to change your level of access at some point in the near future. So the administrator will create some sort of method, usually a ticketing system, to determine what access is later needed. Now, it's also important to remember that you should not always leave the access as is. For example, let's say temporarily the machine learning engineer needs access to the training data that the data scientist has for whatever reason. Once the machine learning engineer has completed his or her task, that access should be removed because the machine learning engineer should not be responsible for that part. Whatever temporary requirements that they required, once those requirements have been met, they should be removed. So, how do you know if somebody has been given too much access or too little access? Well, essentially, that's where we have our auditor role. Our auditor would generally only have read-only access to all tasks, but they will be able to review who's doing what. By reviewing this, they can make recommendations saying, well, I've noticed that the ML engineer has requested data access several times to the training data set. We might need to change that so they don't have to request that access every single time they need it. So maybe we'll need to make that change there. Perhaps also the data scientists might need to do a couple pipeline deployments or assist in some pipeline development. Again, the auditor will review that and make the recommendation saying, this is the access they should have, this is the access that they shouldn't have. So here you really have two people giving access. You have the ML administrator and the auditor, who's not really giving the access, but is giving the recommendations. So remember, least privilege access principle is one of the most important things in cloud, hence AI as well, especially if your AI is running on the cloud, as we're doing here. And also remember, one of the main reasons we want to give least privilege access principle is because quite often users will switch teams or leave the organization, and that email address may not have been removed, which can cause massive security issues in the future. So by ensuring least privilege access, you're always making sure that the access given never exceeds what is required. And the auditor will always review to see if everyone has the correct access and make recommendations to the administrator of that on if that access should be changed. Now, let's talk about granular access to AI resources. So we will all have our own duties. So we need to enforce that separation of duties. We rely on granular access controls for AI resources. The reason we rely on granular access control is because, again, we're following that least privilege access principle, which means we're going to give as little access as possible to the necessary resources we need. So we don't want to just give to somebody, hey, you're an editor or you're admin or you're a writer. No, we actually want to go very detailed saying you're an editor to what, for how often, what time. So if you look at this matrix, we have some visual indicators. We can see how different roles map to different resources. For instance, customer service requires full access to models and feature access. So the customer service agent needs to be able to access the model and needs to be able to access the features. Why? Well, because they're going to communicate with the model, and that model might come with features, or that application might come with features like download PDFs and such. Now, this access can be time-based, meaning that maybe they only have access to certain features while they're processing the customer request. Does the customer service rep need data access? Unlikely. The reason that they don't need data access is because they shouldn't be touching the underlying data and making modifications. So they're in a non-technical role. Let's look at the research assistant. The research assistant might need model access and might need data access, but might not need feature access. Their access can be infinite because they might always need to conduct research or modify data or test the model or even use the model for their purposes. Now, the researcher will essentially need to make sure that they can always access their data and modify it. So you might need to give them full access to make those modifications. Now, actually, it's very interesting with the research role is that the research role and the customer service role don't actually need to be a human individual. It can actually be a sub-agent with these permissions. And especially if you're giving the sub-agent these permissions, you want to heavily control what these sub-AI agents can do. Now let's look at this other matrix, this other row, which is the regional. Regional here might have model access, might not have model access, might have data access, might not have feature access, and is time-based. So the regional administrator in this case is someone responsible for making sure that everything is working correctly for that region. So they might need to test the model, but they need to make sure the data is relevant for that region. For example, if the data is for the United States, it must make sure that the data that it's using is for the United States. Now, should the administrator be able to make changes to the data? No, but should he or she be able to audit the data to recommend changes? Yes, that is actually a possibility and potentially a requirement. So remember, with AI resources, we always want to leave the least level of access possible, control at a very finite level, what are they accessing and by how much, and even create time-based restrictions. One popular time-based restriction that I give is that I usually don't allow any feature updates or access on weekends. So one time-based restriction I do is the user can only make changes between the Monday and the Friday. So let's now discuss zero trust. What exactly do we mean by this? Well, to enforce this matrix, we use a specific suite of AWS services for zero trust architecture. This is the core AI system that is protected on all sides. Here, what we use is we deploy AWS Identity Access Management Identity Center for rigorous user identification. So what do we mean by zero trust? Well, zero trust architecture is ensuring that only when you've successfully been authenticated through rigorous user authentication, you can use our AI system. The way we do this with AWS is by deploying a series of tools. For example, we deploy Amazon Guard Duty for continuous threat detection and anomaly monitoring. So when we're using LLMs, very likely people could write nefarious prompts. These prompts could allow a data leak, a model misbehavior, or potentially something worse, like having the model perform an action it shouldn't do, like sending someone's bank account balance. So guard duty makes sure that not just is the user authenticated and correct, it also checks are any of these prompts potentially running a risk to our system. Guard duty also comes with anomaly monitoring. For example, let's say our average usage at 3 a.m. is 20,000 prompts per minute. Now, what happens is that we got 2 million prompts per minute. That would be an anomaly. And in that anomaly, you can actually use it to say, hey, something is going on, and it could potentially block access for that user, alert anybody that needs to be responsible for that system, or potentially shut down the system. We also have AWS's WAF, which is essentially our web application firewall. This is essentially our first layer to avoid any intrusions and make sure that we are handling requests correctly. For example, are we getting requests from a regionally blocked country? Are we getting requests from regionally blocked devices? Sorry, from technologically blocked devices such as bots. So our web application firewall makes sure that we can control this very well and see these alerts. Then we essentially have our Amazon Identity Center. Our Identity Center is responsible for authenticating our users. These days, we often see user authentication with a two-factor system. So two-factor authentication, like getting an SMS or Face ID or passkey. So Identity Center will allow us to implement this and check. Identity Center also comes with detection software to make sure that the user is behaving the way they are. So it doesn't just look at your 2FA, but it looks at, is your behavior different than before, such as accessing from a strange location or prompting 2 million times per second, which is very unlikely for a single user. And finally, we can set up a private Amazon cloud that runs everything using Amazon VPC or Amazon Virtual Private Cloud. This allows us to create an isolated network. What do we mean by creating an isolated network? Well, creating an isolated network means that we're only allowing authenticated IP addresses or MAC addresses to use our system. So if you are not on a listed IP address or MAC address, it's very unlikely you would be able to use our AI system. This gives us complete network isolation if we have to protect the usage of our data, AI system, or full application. Now let's discuss Amazon Bedrock guardrails. This is one of the most powerful managed features for AI safety. Amazon Bedrock guardrails allows us to automatically evaluate prompts and model responses from foundational models, agents, and knowledge bases. What do we mean by this? Well, first let's talk about why we need a guardrail. A AI guardrail is making sure that the model does not give a terrible response, an illegal response, a dangerous response, but it's also making sure that the model is not ingesting a dangerous prompt, an illegal prompt, or an unauthorized prompt. So earlier slide, we discussed how we can build an infrastructure security layer. Here, we're going to talk about how we can build an AI security layer. So how exactly is this going to be done? Well, guardrails, you can write rules that allow the model to learn on what to do and what not to do. For example, let's say somebody always asks a prompt that says, tell me this user's balance. Well, we know they shouldn't be doing that because you can only see your balance. So what you can do is that you can actually teach the AI that this is an inappropriate prompt. Why would we teach this with the AI using guardrails? Well, let's say somebody changed that prompt slightly and says, is there any user balance you can share with me? Because it had learned that the previous prompt, tell me this user's balance, is not correct, it can inferred that prompt that they're asking, can you tell me any user's balance, is also incorrect. So we do this by defining topics with short natural language descriptions. We tell Bedrock what not to talk about, but we also tell Bedrock, hey, this prompt is potentially a risk, and Bedrock learns from that. It's almost like labeling prompts and outputs to determine what should be shared and what should not be shared. Now, what happens if in our knowledge base we accidentally uploaded some data that should not be shared and we're not aware of that? Well, Bedrock automatically comes with personable identifiable information removal systems or other sensitive information systems. So what is personal identifiable information? Well, personable identifiable information is information that identifies a user, such as first name, address, phone number, credit card, or ID number. This allows Bedrock to catch this in case you miss it. We're all human and we make errors, but Bedrock will be able to identify personal information across a number of systems worldwide and across a number of IDs. It can recognize IDs from several countries. It can recognize credit card numbers from several providers like Visa, MasterCard, or American Express, and make sure that information never does get leaked in case it got accidentally leaked. It can also protect against sensitive information. So let's assume the user asks a question like, how do I write a piece of malware that will allow me to crash 200 computer systems, right? Well, it can actually identify this is a sensitive topic and never let it get to the model. So that way your model doesn't even have to think about answering the question. It will just stop completely. Besides writing these rules, prompts, and examples, you can always apply a set of keywords to detect and block. For example, if someone uses the word hack or malware, you can immediately block it from the prompt. Ask the user to rephrase if they mean something else, block the user, or just limit the prompting for that current moment, or just simply also alert the user saying, hey, actually, I'm not allowed to discuss that topic, so be careful with how you word it. And if they word it too many times the same way, you can actually block. So Amazon Bedrock Guardrail is our system. It sits at the layer of where our model and application will sit. So in between our model and application, ensuring that you can add AI safety features to your model. So let's actually see an example of how Amazon Guardrail works in more detail. Using this particular diagram, we're going to see the execution path of how Guardrail works. A user provides an input to Guardrail. In this case, it would be a prompt. Bedrock or Guardrails creates a invocation via the invoke model or converse APIs. This will essentially apply the Guardrail API. So what's happening here is the Guardrail API is being implemented once the user provides the input. So as you can see in one, once it gets to Bedrock, Bedrock is going to go to the first guardrail check. Inside that guardrail check, it's going to check, hey, is there any content filtering? Like for example, I'm not allowed to talk about this particular subject, country, person. Any denied topics? Any word filters that I should be filtering out, such as malware, hack, any sensitive information filters I need to apply, such as is a user implementing first name, any contextual grounding check, which we'll talk about in just a second, or any augmented reasoning check, which we'll talk about in just a second as well. So what is a contextual grounding check? This is different compared to the other ones. The other ones are pretty straightforward to understand. Well, contextual grounding check means, is the information I'm giving correct? For example, if somebody were to ask a prompt, who won the Super Bowl in 2026? And the answer was last year's Super Bowl winner, or contextual grounding check would check through different sources, such as news sites, and say, hey, this is actually a question this answer is incorrect because I just checked out the site for some of the popular sports networks and I can see that it was not the correct answer. So let me fix it. Contextual grounding is essentially how we do checks to make sure we're providing the correct answer. What is an augmented reasoning check? Well, an augmented reasoning check is when the model is going to take a higher level approach or a more deeper thinking process to answer the question. So, for example, let's say you asked it a mathematical question. It'll say, okay, this is my first answer, but let me break this down to smaller steps. Let me rerun it one more time and see if the answer changes. And if it does change, that means that you did it correctly. If it doesn't change, then if it does change, that means you did it incorrectly. If it does change, if it does change, that means you did it incorrectly. If it didn't change, that means you did it correctly the first time, and the model will respond. Now, as you saw, this guardrail is being implemented at step 1 and 2 once the user writes a prompt, but it's also implemented at step 3 at the output stage, because all these checks will also occur at the output stage before it gives a final response. Because if you remember earlier from several slides, our investment advice agent was responsible for checking, is this prompt okay? And also checking if our final response okay. So our investment advice agent from earlier slides, it was actually using guardrails to answer the particular prompt. So guardrails is already available to us in Bedrock. So we don't have to worry about creating logics and elements to apply these checks. We can actually just use guardrails in Bedrock. So let's see some popular use cases for guardrails. One use case could be maintaining AI safety across multiple applications. In the real world, people will try to use your AI in nefarious ways. One of the most common ways to use it is to try to get information about your model. Sometimes this is not just personal identifiable information about your user, but how is the model built and how is the model trained? For example, if I know how your model is trained, I could potentially manipulate it. If your model tells me that it scrapes a certain site every year, then maybe I can change that site's content. If your model tells me that it reviews its step, like every answer it gives by following this step structure, maybe I can say, skip this step in your structure. So we need to maintain AI safety. And what guardrails does is that it can actually apply through a series of word filtering and checks. Is the person asking too much information about what the AI does? Guardrails also checks the application that you're running in. So if you're running in a banking application where security is paramount, it can actually check there, am I running in a bank and should I limit my response because I'm being deployed in my bank, or should I double check before I give any answer, or should I always limit my answers to a certain extent? After this, it can actually block undesirable topics. Now, undesirable topics are usually topics that you don't want to address. These could be topics like self-harm topics, hacking topics, crime topics, and such. Now, a lot of nefarious users are quite clever. So they might actually say, not how do I steal or hack into your website? They might say, what protections do you have against hackers, and work their way from there. So what these undesirable topics do is say, if anyone mentions the word hack or the topics about hacking, just don't answer it. Go back with the typical response. Guardrails also filters out harmful content. So let's say you were creating a model for generating some sort of press release or creative content for advertising. Well, to avoid creating any racist, dangerous, violent content, these models are protected. So if you were to ask it to create some sort of racist content, it would actually not do that for you, because guardrails is there to make sure the content is not harmful. So it protects your user and your brand reputation. It's not always just about creating harmful content. What if I wanted it to manipulate a photo? For example, what if I wanted to take a popular picture and add a fake image behind it? Well, what guardrails will do is check to say, hey, I'm not actually allowed to manipulate this picture, or say you're trying to manipulate the action of a human being in real life. So I'm going to try to create a protection around it to make sure you cannot do it. Guardrails comes with content filtering already enabled. There are ways to limit the content filtering, but they will always be available, particularly to violent, racist, illegal questions. And finally, of course, redacting personal identifiable information to ensure compliance with privacy laws like GDPR and CPA. So guardrails will automatically redact this information. A lot of users sometimes might ask medical questions. Oftentimes, these models cannot respond to medical questions because they are protected by the HIPAA privacy law. So it might actually not answer the question correctly or limit its response. But it will also make sure that it's not giving any information out. For example, if I were to ask the model, hey, what's my insurance number? It might actually redact that information in the database and say, I apologize, I cannot give you that information. Please contact your provider. So this way, it's making sure that any PII information is redacted before it sits in there. Laws like GDPR are actually quite strict, and the penalties can be anywhere between 4,000 to 40,000 euro per violation. So it's important that your model redacts personal identifiable information immediately. And in case the user tries to create, modify, or extract personal identifiable information, guardrails will ensure that this does not happen. And it also gives you a confidence score of how likely this is PI or not. And then you can set thresholds saying that if you have a even 10% likelihood this is PI, don't share. Or if you want to be a little bit more strict and say, hey, this is only 90% PI certainty block, or you could say even 10% PI certainty block as well. It's completely up to you. So we looked at some use cases. We discussed what guardrail can do. So now let's actually look at an application example of guardrails. Here what we have is an example application architecture highlighting defense in depth security. This is when the user submits user input like a prompt via the demo website application frontend. Then what happens is that it goes through Amazon's API gateway path. Remember, the Amazon API gateway path is defining which which API endpoint gets the prompt. This will then go to an AWS Lambda application connecting to a prompt template and application logic. Remember, the Lambda application is responsible for processing the business logic. It's responsible for then saying, okay, I have this prompt. What do I need to answer this prompt? Or do I already have enough from the first layer to answer this prompt? Notice here we have something called prompting protection. Prompting protection is done at that Lambda level within Amazon Bedrock's guardrails. What will happen here is that prompt will go to our first layer of guardrails, which is this prompt safe to answer? So if the user asks, let's say, a corporate hacking question, we can immediately respond saying, actually, we can't answer this question, please rephrase, or I'm not allowed to talk about hacking. Now, if it makes it past the input guardrail and it goes into the output guardrail to our foundational model will then look at its knowledge base, look at whatever tools we gave it to answer the question. And then it will go to our output guardrail. So our output guardrail is not so much to measure the quality of the answer, it's more to measure if there's any dangers in providing this answer. So again, going back to our hacking question. In our hacking question, we can actually see, okay, we're giving a hacking response. Somehow it got through our input guardrail because of a clever prompt. Should we even answer this question? Or I can answer it, but now I'm giving too much sensitive information. Let me redact it. So the output guardrail is now double checking to make sure that everything works. Let's say the user in this stage asked a question about someone else. Before it gets there, it can actually, before it returns a prompt, it can actually respond saying, actually, you don't have the right information because it checks our identity access management at the bottom. By checking this, it's actually saying, hold on, this user is asking about another user. They're not logged in with that other user's account. They don't have permission to look at that other user's account. So let me respond by saying I can't answer that. So remember, we have two levels of AI guardrails happening. The input, which is checking, can I even answer this? And the output, which is checking, I've answered it, is that answer safe? And then it all goes into our Lambda function, which will process it back. Now remember, we were just discussing guardrails, but earlier we also said there could be quality checks that can be done at the at the application front-end layer before it gets sent off, or at the AWS Lambda layer, which is more likely before it gets sent off. So this will be a quality check. And remember, I stress that guardrails are not quality checks of response. They're checking if the response is okay or dangerous. Input guardrails are not about checking the quality of the prompt, like can we summarize it, can we make it smaller, can we make it more efficient? No, it's about checking, can I even answer this prompt? Should I answer this prompt, or do I need to alert somebody or respond to the user that I cannot answer this prompt? So in this architecture, if we were just to summarize it, we have our front-end application, our Amazon API gateway that sends the prompt to our Lambda function, depending on what endpoint that's going to call. Our Amazon Lambda function, which applies our first layer of prompting protection. Then it goes through our input check. If it passes the input check, it goes to our output check. If it passes the output check, it goes through our application backend. And then after that, it goes through one final step before it gets back to our application frontend. So one of the great things about a Bedrock guardrail is, again, it has a lot of solutions and guardrails already pre-built, so we don't actually have to build them ourselves. Now, let's actually talk about applying a real-world architecture blueprint for AWS native agent systems. So this diagram represents the pinnacle of what we learned today. It is actually a blueprint for a multi-agent library assistant using Amazon Bedrock, AWS Lambda, Athena, OpenSearch, Glue, and S3. So let's talk about what is going on here. The purpose of this system is to help the user with any library queries, such as finding the correct book, making sure that they're not late on payments to the book, making sure that the book has been returned, and all these elements. So the goal is to respond with a proper library text query back to the user. We'll input a piece of text, we'll output a piece of text. So the first element you see is a library assistant system. This is our front-end application, right? Then from here, we go to Amazon Bedrock agent. This is our first supervisor agent. Now, what is happening at this first supervisor agent? Well, it's going to take the user prompt and then determine where the prompt needs to go next, right? And remember that at this stage, we're going through our first input guardrail. So at this stage, we're checking, is this prompt safe? Either based on our rules or the default guardrail rules. Once it goes to the Amazon Bedrock agent, the Amazon Bedrock agent can then send it to three potential locations. SQL agent, which will very likely research some sort of SQL database. The library agent, which will collect a knowledge database, which will contain books if we're asking for which book should we use, or our essay agent, which will help us write the essay. Now, notice how the essay agent doesn't just act on its own. The essay agent actually connects to a knowledge base because maybe it needs to reference books, maybe use books as an inspirations to write the essay. So let's first continue with this journey of the essay agent. So our supervisor agent determined, hey, the user needs help writing an essay. Let's pass it to our essay agent. Remember here, we're going through our guardrail checks as well. Then it goes to our knowledge base agent, again, going through our guardrails checks as well. And it's going to look at that knowledge base using Amazon OpenSearch. So if I need help writing an essay about AI safety, then it can check, do I have any resources in my knowledge base using Amazon OpenSearch that will help me answer this prompt? Then it sends the content, which will be from our knowledge base, to the essay agent, and the essay agent will then start to formulate its response. Remember that our data doesn't always have to sit in Amazon Open Search Service. It can also sit in S3 buckets, which very likely, if there were books, they will probably be in a PDF or EPUB version, which will sit in an S3 bucket. Now let's take our journey a little bit different. Let's go to our library agent. Our library agent, again, with guardrails, will then go to our Bedrock knowledge base agent. What if it was to check, hey, is this book even available? Now, would this information be in our open search service? Potentially could be. Very unlikely it'll be in a bucket. But where could it potentially be? Well, it could be in an Athena database, which is connected to our S bucket. So our Athena database is passing maybe a data set of book availability to our knowledge base, and our library agent collects that information. Now let's talk about the SQL agent. The SQL agent might get a prompt like book availability, how many books are available on the subject of AI safety. So why do we use a SQL agent here? Well, we use a SQL agent because we want to use a database. Knowledge base is usually unstructured data, right? Like textbooks, images, PDFs. Usually, it can be structured data like CSVs and Excels, but a SQL agent always deals with structured data like databases, Excels, and CSVs, which will always be in some sort of SQL database. So the SQL agent will execute the query based on the natural language response it got from the supervising agent, right? So supervisor agent will say, hey, how many books on AI safety do you have? SQL agent will then pass that natural language response to our Lambda function, which will execute our SQL query. Now we have the Lambda function going into two directions. It might go to our Athena library database, which is relatively quick, or it might go to our Glue data catalog, which is a more complex style database, depending on what we need. What's the advantage of using AWS Glue in this case? Well, AWS Glue has additional features to give us the metadata to help answer a prompt, saying, well, actually AI safety falls under IT security, so this might actually be, we have a total of 1,000 books on IT security, but only 100 on specific AI safety. Our Athena database might just count how many books are actually part of the AI safety category and return that back. So the Bedrock SQL agent is responsible for determining which element, which would be our AWS Glue or Athena database, gets. Now remember that our Athena database might just have more basic information. I don't want to say the word basic so much, but as straightforward information. And our AWS Glue would have more metadata and potentially faster filtering requirements. So once these responses get connected, they're passed back to the Lambda function, and that Lambda function then sends it to the Bedrock agent, which then gets returned to our library system. Now, is it possible for all three agents to handle the query? Yes. Let's assume that I write a more complex query. Let's say my query is I need to write an essay on AI safety. How many books on AI safety do you have? Which books on AI safety do you recommend if my topic is AI safety on AWS? And suggest which books I should reference. So now we know we need to go to our knowledge base, we need to go to our SQL agent, and we need to go to our essay agent. All three can actually work together, technically all four because we're including knowledge base, and then passing it to a supervisor agent. The supervisor agent will review all the information and make that final determination to see if we connect it to our AI system. And if it all passes the checks, we send it forward. Now, what is also something great about this infrastructure here? Notice how we each have individual agents, right? This is a multi-agent system. Each agent can use a different model. So for example, the SQL agent needs to write SQL queries. Should we use a large language model like Gemini Pro or GPT-5? Maybe, but unlikely. We could use a much smaller and faster model to do it because it only has to write the SQL code. So it just has two responsibilities. Understand what the natural language query is and convert it to a SQL. The library agent can also be a different model. Remember, the library agent is primarily responsible for maybe answering frequently asked questions about the library and maybe looking up books. This one could be a little bit more of a large language query, but doesn't have to be a large language model, to be honest. It can actually be a relatively small one. Then, of course, we have our essay agent, which is very likely going to be our large language model. Again, doesn't have to be, but very likely will be. Why would it be? Well, it might be because writing an essay is actually a complex task. It's not just putting words on a page. It could write gibberish on a page. That's not an essay. It needs to think about the structure, the theme, breaking it up into paragraphs, maybe how many paragraphs it needs to write, first person, third person point of view. What is the overall goal? Citations, because if it's not doing citations, it could be plagiarism. So our essay agent is actually responsible for determining all these steps. So it's very likely this one will be a large language model. And it might use the information from the other agents to help put it all together. Our supervising agent could also be a large language model. Why might it be? Well, remember, our supervising agent has a responsibility of determining where the next task goes to, where the prompt goes to. It very likely will be a large language model because it needs to think, which agents do I need to help me solve this? Also, it has the responsibility of managing the prompt as it comes in, maybe adjusting it to make it shorten. It also has a responsibility of reviewing the prompt before it gets, the output before it gets sent out to make sure it doesn't overload the system or give a bad response. And on top of that, it's got all its guardrail implementations. Now, again, these are essentially just suggestions, but it all depends on your particular use case and scenario. So here we have a multi-agent system using different LLMs, different guardrails, different knowledge sources like S3, Amazon Open Search Service, AthenaDB, AWS Glue Data Catalog, and Lambda functions for processing information queries and outputting information queries, all connected to our front-end application library system that is getting its input from the user. So overall, we are using Amazon Bedrock, AWS, Athena, OpenSearch, Glue, and S3 to build our complete solution. Well, I would like to thank everybody for your attention and engagement today. We've covered a tremendous amount of ground from fundamentals of serverless generative AI to highly secure multi-agent architectures running natively on AWS. Again, I thank everybody for joining this webinar, and I wish you all the best. Thank you. And that is it.
Thank you, Francisco. That was very informative. To give the presentation rights over to Remy, our vendor manager, to introduce our promotions and webinar-related courses.
Thank you, Tracy. I believe everyone must have learned something new today or would have been able to brush up their skills around the fundamentals of AWS Cloud. I would quickly like to take you through some of our hand-picked resources, which we think will immensely help in accelerating your AWS Cloud scaling journey. Well, this document here of sharing on my screen, this has been shared with you all in the handout section of GoToWebinar panel. You can download this document and access all the resources and browse all the offerings we have curated for you. So first up here is the list of our recommended courses, which we feel will best suit your learning journey after attending our masterclass. All these courses are hyperlinked. Feel free to go through them post-event and check out the course descriptions, prerequisites, and the value it can add to you and your team's skill sets. Additionally, we have curated a blend of resources, including our upcoming and on-demand events, as well as informative and educational blogs. You can make the most of these resources to gain extensive knowledge on the AWS topics they cover. Our free AWS e-learning courses follow a self-paced training model wherein you get the liberty of accessing extensive course-related videos that are delivered by the AWS subject matter experts on the go. So these videos cover the availability on the device of your choice, so you can access them from your laptop, your tablet, or from your phone as well. There are more than 280 videos covering various AWS topics explained in a very easy to comprehend language. You can simply sign up for free, watch these videos, and make the most out of them. Also here, I would like to inform you that this session is being recorded. So in case you want to refer back to any of the topics that the trainer might have covered in today's session, we will be sharing the recording link with you through emails, and also you can access it here by clicking on this button. So you have to download this handout for that, and then if you want to revisit any topic, you can just simply click on the access recording and you can revisit the session and learn at your own pace. Now, apart from our virtual sessions, you can also catch the relevant updates related to IT and business trainings on our social media handles. So please feel free to follow us on LinkedIn, Twitter, Instagram, and subscribe to our YouTube channel for all the latest updates. Our official pages and channels are linked here on the icons. Finally, if you have any suggestions regarding the topics you would like us to cover in our upcoming webinars and masterclasses, please don't hesitate to send us a direct message, or you can leave a comment on our social media posts, or you can just simply email us at info@netcomlearning.com. We would definitely try to come up with the sessions on your suggested topics. Thank you once again for joining us today. Over to you, Tracy.
Thanks so much for guiding us through that information, Remy. And now we're going to go ahead and jump right into our question and answer session. First question is, what makes an agent-driven workflow different from a traditional serverless workflow?
So an agent-driven workflow and a traditional serverless workflow really differ in the complexity and the different number of tasks we need to do. So a traditional serverless workflow usually relies on linear pre-programmed executions, right? So essentially what we're going to do is that where the user is going to make a call to the front-end application, it's going to route it to the Amazon API and to an AWS Lambda function most likely, and it's going to apply very strict and explicit application logic. Then it calls the foundation model and gets a response. So essentially, we're not giving it that many steps. We're saying, here's the task that you've been chosen to do. You're going to complete this task by following these very strict instructions and give the response. So it's not very flexible. Now, an agent-driven workflow uses the foundational model to figure out what are the additional agents or tasks it needs to answer the prompt. So the agent can then decide what knowledge base it needs, what other Lambda function it needs, what specific action groups it needs to complete the task. So it has more flexibility and more dynamics on how it can behave and such. So it can handle a wider variety of questions and prompts or tasks, whereas a traditional serverless workflow is essentially just one geared to answer one specific task and give a very strict response. So you wouldn't really use a traditional serverless workflow for a general knowledge solution. An agent-driven workflow could do it.
Second question, why do we need a supervisor agent in a multi-agent architecture?
This is a great question. Now, in a complex system, the supervisor agent acts as an orchestrator. It is checking to see which model or subagent is best at answering this question. So if you will, it is a decision maker. It will check to see, okay, which model do I need, which task do I need? And then it will delegate those tasks to the subagents. It might route it to a SQL agent, as we saw earlier, or to a library agent, or it might route it to both of them if it needed to. The supervisor agent then will take the response and determine, is this response good? If not, I might need to ask the user to wait and then send it back to the subagents to get a better response. And maybe this time it includes another subagent or includes fewer subagents. So essentially, it is the one that is managing everything. A good way to think about the supervisor agent is kind of like the project manager. It's saying, okay, who do I need to complete this task? Great, I have the team. Is the task completed? Is it quality? Great, I'm going to send it off to the user. So that's why you would need the supervisor agent to manage the other agents.
Next question is, how does Amazon Bedrock integrate with AWS services without directly accessing data sources?
Yes. So Amazon Bedrock relies on intermediary components to securely abstract data access. For example, action groups. Bedrock's agents can use action groups that invoke Lambda functions to execute specific logic. For example, if a Lambda function can securely handle a SQL execution by querying it in a database and then map it to AWS Glue. So here what you're seeing is that the Lambda function is using the database and AWS Glue securely, meaning that you cannot invoke that Lambda function without having access to it, and that Lambda function will carry out very specific instructions through SQL execution and AWS Glue to make sure that it returns the appropriate response that it has access to. Now, let's think about this for another data source like knowledge base. Instead of querying the raw data source directly, like reading an open PDF, agents search a structured knowledge base. So what is a structured knowledge base? Well, it is essentially a knowledge base that's already cataloged with metadata and information. So let's say, for example, you're doing a library agent and you ask it a computer science question. It doesn't need to read every single book to understand that it's a computer science question. You've already have in the metadata computer science information catalog. Now, what the knowledge base does is that it actually has this information in some sort of vector encryption to make sure that the data is securely outputted out, meaning that it doesn't output just gibberish. And if anybody were to get unauthorized access somehow to that database, they would not be able to see the content correctly. They would only see like abstractions or encrypted data. So it makes sure that it uses Amazon OpenSearch, which is a serverless index, and it feeds that information directly back to the user in a secure fashion. So AWS does give you the ability to query structured databases through AWS Lambda functions, Athena database, and AWS Glue securely, because you can only access those databases through functions that are approved. And it also gives you the ability to access knowledge bases like PDFs and such and images in a structured uh, knowledge base, which is connected to OpenAI's, OpenSearch serverless index. And OpenSearch serverless index makes sure that everything is encrypted and secure before it gets sent out.
Next question in the queue is, how does this architecture scale when user demand increases?
So the system relies on serverless architecture like we saw. Like a Lambda function is serverless, meaning that it will scale to meet the current demands. Amazon API Gateway ensures that it has the correct level of access and it handles the different load requests. So it's not always pinging the same endpoints if it sees that one endpoint is being overloaded. Now, pretty much most AWS services have auto scaling policies. So that means that it's using some sort of predictive scaling logic to determine how many resources you need. Now, earlier we talked about that you can put a limit on those resources. Say you say a limit of 100 machines, right? It'll never be able to scale past 100 machines, but it can scale anywhere between 1 and 100 machines to meet your request, depending on usage patterns. So this architecture ensures that you're not actually managing the hardware. You're not in a situation where you're like, okay, I need to understand right now that I need to increase to 100 machines. So I need to send that request or write some logic for it to understand. AWS predictive scaling will learn from your usage and scale accordingly. And as I said earlier, it might even make recommendations saying, actually, I think 100 machines will make us hit our limit soon based on the past performance of the last 2 months. I recommend you raise up to 200 machines. And then you're the one who decides to raise up to 200 machines. So rather than you writing business rules and logics to enhance scaling, it will learn from your users using your system and handle the scaling itself through Lambda functions, API gateways, or other tools that all have serverless logic applied to them.
And the final question is, how are security and responsible AI handled in this agent-based system?
Yes. So most architecture uses a zero trust AI model that relies on, any service that relies on AWS uses a zero trust AI model. This means that it's always checking who you are, what you're trying to do, and where you're trying to get. It essentially saying it doesn't trust your system. Sorry, you by default. So you have to earn that trust. How is this trust earned? Well, first you go through AWS Cloud Identity Management or the Identity Center. This checks, are you an authorized user by looking at your email, password, what other factor authentications you might have. Then remember, Amazon Guard Duty checks for threat detection, looking at your location, your prompt, your usage. Then we have AWS WAF, which is for web traffic filtering, and it will check to say, are too many requests coming from you? Do I need to filter this web traffic? Is it coming from an incorrect system? And then finally, you can build your own virtual private cloud across your system, which allows you to make sure that your agent is only used by authorized users. So you have the layer of checking. Can someone use this AI system? Two, what are they trying to use from this with this AI system? Is this already a known threat? Three, are they coming from a location that we know is safe or a location that is potentially dangerous? And then finally, four, which is, are they authorized to use our virtual private cloud via their IP address or MAC address? And then of course, access by default is enforced with the least access principle, meaning that You should only access to whatever you're limited to access at the smallest possible scale. Now, that's the technical side. Let's talk more about the contextual side. Amazon Bedrock Guardrails applies responsible AI. It checks the user input to say, hey, is this a question that I'm allowed to answer? Is this a prompt that I'm allowed to answer? And it also checks the output, evaluating through context filters, denied topics, word filters, rounding checks to check the quality of the answer, like if it's correct, and make sure that it blocks any personal identifiable information. So Bedrock Guardrails applies the responsible AI elements, making sure that the AI is being used correctly and safely. Whereas the other applications I talked about, like Guard Duty and Identity Center, are there to protect the infrastructure, making sure that it's scalable, reliable, and no one is getting unauthorized access through nefarious means.
Once again, I want to remind you that as you leave this session today, you will be presented with a short survey. We would like to request for you to help us by taking a quick moment to participate in that survey. Your feedback really helps us understand your learning experience as we are constantly looking at how we can improve our future sessions. The survey answers are measured on a scale of 1 to 5, 5 representing outstanding and 1 representing poor. We want to thank all of you for joining us today, and if you do come up with any additional questions, feel free to send them to webinar@netcomlearning.com at any time. We hope that you found today's webinar informative, and we look forward to seeing you back here with us soon. Feel free to tell your friends and colleagues about our webinars and other courses. Have a great day, everyone.